All right. Hello. My name is Aiden. This is the second lecture in our 5-course lecture series on approximation. Yesterday we talked about approximating real numbers with floating points, which is, I think, a pretty good place to start. But today we're going to be moving on to talking about a subject that I care more deeply about, which is polynomial approximation. And we're going to do this through the lens of a method called polynomial interpolation. So again, the overriding goal of this whole series is to take objects that we don't understand or that are hard to quantify or analyze and approximating them with objects that we do understand or that are easy to quantify or analyze. Yesterday we talked about doing this with real numbers, but today we'll be doing this with functions, and we'll be approximating functions using polynomials. So this is kind of our the breakdown of what we're going to talk about today. So first, I kind of want to start with a little example. So if we have some dots in two-dimensional space, we want to connect these dots with a curve. I think everyone here has done some sort of connect the dots as a child, and so we're basically just playing connect the dots again, but this time we want to do this in a rigorous way, in a mathematically interesting way. So what strategy are we going to employ? Well, when I say connecting the dots, what I really mean is I want some sort of function where it takes in the first value, this x0, and it's going to output the second value, like the y0. So like f of x1 needs to be equal to y1, f of x2 needs to be equal to y2. I'm sorry, this should be from 0 to n. And we want to have this curve. Now, I've called it a function f, and you might remember a rule about functions, which is that a function cannot map the same x value to two different y values. So in order to make sure this can't happen, we're going to assume all the xi's are different. But other than that, there's no constraints on the input or the output. So we're just assuming that we have distinct xi's, but potentially or probably different yi's. So like one particularly easy thing we could do is to just connect these points with straight lines. So just take all the dots and connect them with a series of straight lines. And we'll get back to this, I believe, tomorrow. But this approach has some downsides. And the biggest of these downsides is that the function we get will be spiky, which is something that we want to avoid. So if I can switch my stream, I'll just stream my entire screen, I think. Can you see the paint? Thanks. Okay, so if you imagine we have these points, you could just connect these all with straight lines, or as straight as I can make them. But what you'll notice here is we get this like spiky behavior. And for various reasons, these spikes are bad. For instance, if you were to move a person along this very spiky path, at each one of these spikes, they would experience quite a bit of jostling. They would basically experience quite a bit of force to move them over those spikes. So we want to avoid these spiky paths, and instead we will prefer to use paths that are smooth. And among all the smooth functions, like the nicest ones are probably degree n polynomials. So the goal is, if we have n plus 1 points, which we do, we want to use a degree n polynomial that goes through all of these points. Also, you can ask questions if you have any. Just I am looking at the chat, and I am also, you can unmute and ask. Okay, so I'm going to outline our approach real quick so that there's some structure. I want to show you first that this problem is always solvable. If you give me any n plus 1 data points, then there's going to be at least one degree n polynomial going through them all. Two, I want to show you that this polynomial is unique. It is, if I give you n plus 1 points, there's only one degree n polynomial going through all of them. And three, that this polynomial can be computed and evaluated quickly and accurately without ever writing it down in the kind of standard form that you've learned polynomials in. And so to do this, we're going to take an approach that is sometimes viewed as inferior, but is actually quite superior if you know what tools you're going to do. And in particular, we're going to need some tools from algebra. Okay, sorry, my next thing was getting weird. So we're going to define this thing lambda I to be this kind of absolutely nasty looking polynomial. But it's actually kind of a beautiful polynomial. Right, we have these points x0 through xn, and my goal in constructing this polynomial is I want a polynomial that is 0 at every xj other than xi. So notice, if I were to plug in, for instance, x0 to this polynomial, well, the term on the left would become 0, and so we'd get a product, but it has 0 in it, so the whole thing's 0. If I plug in x1, the whole polynomial is 0. If I plug in xn, the whole polynomial is 0. But if I plug in xi, then the top and bottom are equal, and they cancel, and you get 1. So this polynomial is going to look something like... that deleted more than I wanted it to. This polynomial is going to look something like, if these are my points, and let's say I want it to be 1 here, then it's going to look something like that. Now that's kind of a potentially bad drawing, and actually it is kind of a terrible drawing, because I actually, now that I'm looking at it, I know exactly what this looks like this. And this value here is 1, but at every one of the other values it's 0. Does this polynomial make sense? Like, we've constructed this polynomial specifically to have the property that it's 1 at a single point and then 0 at all the other points that we care about. And this lets us do kind of an immediate trick. Yeah, again, at all the points other than xi it's 0 and at xi it's 1. And so we basically are done. We have now found we can very easily now find a polynomial that satisfies this equation that lambda xi equals yi by just summing all of those lambda i's. Because if I multiply lambda I by yi, now it's going to take the value yi at xi and then 0 everywhere else, or 0 at all the other points. So we're basically scaling our my computer is lagging. We're basically scaling our polynomial to make it equal to yi at the top instead of 1. And then when we add them all up, we get exactly what we want. And like, this is, I think you have to admit, a pretty neat trick. Is my audio doing weird things? Maybe. So sorry, there was a question. So by doing this, we can set it to a y level. We want to set it 1. Yes, exactly. So we first get it to give us 1, and then we multiply it. And so at the point we want, 1 times y1 is going to 1 times yi is going to give us yi. But at that point, it's going to be 0, and so multiplying by 0 isn't going to change anything. And so at each xi, only one of these lambda i's will be non-zero, and it's going to have the value yi, which is the value we want. And you can run through the algebra yourself. It's pretty quick. Just do it for like 3 points, and it kind of becomes immediate that like this polynomial does the job that we want. And this is called the Lagrange interpolation method. Now, this polynomial works. I've given you this polynomial and a formula for computing it. It will interpolate your data. It will be a curve that goes through whatever data points you give it. But I have not shown you that it is the only curve that does this, or at least the only polynomial of degree n that does this. And I want to show that now. And to do that, we're going to use a pretty ubiquitous trick in mathematics. Namely, okay, so let's think about a polynomial that's degree n. In algebra, I hope you learned that you can always factor a polynomial using its roots, right? So if you know that p has a root at xi, then you can factor an x minus xi out of it. Okay, so let's do that. Suppose you have a polynomial p, its degree at most n, and p of xi is 0 for all of the xi's. Now remember, there are n plus 1 of these xi's. So we can just factor all of those factors out. And this yields this factorized form you can see on the left, where p of x can be written as a product of those x minus xi's times some polynomial q. Now there are two options. Either q is 0, and if q is 0, p must be 0, or q is not 0. If q isn't 0, then the degree of p must be at least the degree of p must be at least n plus 1, because when you have n plus 1 factors and multiply them, you will get a degree n plus 1 polynomial. But it's not a degree n plus 1 polynomial, it's a degree n polynomial. And so it must be 0. Which is like, I don't know, kind of a beautiful proof. If you have a degree n polynomial with n plus 1 zeros, it must be the 0 polynomial. Period. Done. Argument over. And it turns out this is all you need. What you can say is, okay, well, suppose p is just some a degree n polynomial which has this property that p of xi equals yi, and then we can take the difference between this p and the lambda we constructed. This will be a degree n polynomial because adding and subtracting degree n polynomials doesn't change the degree, or at least it could make it lower, but it can't make it bigger. And so the difference of those two polynomials has at least n plus 1 zeros, and so the whole thing is 0. And if the difference of two is 0, then they must be equal. And so I think this is kind of a neat trick, and it's used all over. Like there are entire like fields of math just about proving existence and uniqueness of solutions to things, and this trick is just used everywhere. And I've even used it in an actual like applied setting, like doing work with numerical methods, trying to prove that two things had to be equal. So it can be a useful trick even in applications. But for now, the most important thing is just that because of this uniqueness, I don't have to worry about saying the polynomial interpolant through these points, because there's only one. There's only one interpolant through them, and so there's just the interpolant through those points. So with these few slides, I have now shown you the first two of the three things that I wanted to show you. Well, at least some of the things. Now, if we go back, no, I went back too far. Okay, if you go back to this list here, you'll see I had these 3 points. And in the third point, there was this potentially strange comment, which is without writing down its coefficients. And so why is this important? Well, it turns out polynomials have a bit of a bad reputation, especially in the field of numerical methods, which is what we're really talking about here, for being a little bit problematic. And it turns out, if you boil everything down, it's almost always a problem of writing down polynomials in their standard form. Basically, we talked yesterday about stability. It turns out the act of computing those coefficients and then computing and then evaluating the function using those coefficients is inherently unstable. So we really want to avoid using those coefficients to do anything. And for computational reasons, if we're never going to use them, we don't even want to compute them. So we want to be able to evaluate this polynomial without ever actually writing down the polynomial, which is kind of an awesome trick. Just like you have a polynomial, and normally you write it in this standard form, but why would you? Just don't do it, and figure out a way of evaluating it in a different way. So that's what we're going to do. We're going to try and work out exactly how you would evaluate this polynomial without ever writing it down in the standard form. And it turns out that this is, well, already kind of done. Previously, we wrote lambda, our polynomial, in terms of these lambda i's as this sum, right? So if there is a good, efficient way to evaluate these lambda i's, then there is also going to be a good, efficient way of evaluating lambda just by summing over I and then evaluating lambda I. So we can boil down this whole problem into just how can we quickly and efficiently evaluate these lambda i's to then be able to evaluate our whole polynomial. So we now have some computations. One thing to note is that these Lagrange polynomials, which we're calling lambda I, they share a lot of the same factors. Basically, the way we constructed the Lagrange polynomials lambda I is we just took a product of all the x minus xi's except for one of them. So we can basically rewrite every single lambda I in terms of this new polynomial L and something I'm going to call the interpolation constant. And so just doing a little bit of math and doing some factoring, we can write lambda I as this product, it's equation number 4, of L of x times 1 over this interpolation constant times x minus xi. And now, don't get too bogged down in the apparent division by 0, because really what we're actually doing isn't dividing by 0, we're doing polynomial division. And so this division just takes out one of the factors in the L. But in this way, all of the lambda i's now have this big shared factor, and the only difference between them is this last little bit. And so we can rewrite our big lambda, our interpolating polynomial, using this new interpolation formula. And this gives us what's called the barycentric interpolation formula of the first kind. All we have to do is compute this first product, and then compute the sum of these terms over here, and that gives us our polynomial without ever having to write down the coefficients of the polynomial. So, are there any questions so far about any of this? Okay. So, this is good, but if we stopped here, we wouldn't have done enough, because there is an even better formula that we can use, which is the barycentric interpolation formula of the second kind. And I'll put my cards in the table. I think I say this later, but if I basically am ever tasked with evaluating any polynomial, my preferred method of evaluating it is to use the second barycentric interpolation formula. It is incredibly powerful, and we'll spend a bit talking about it, but it is very useful, and it is very good. And we're basically, I'm not going to go through and prove it, but it turns out you can do the exact same trick we did for showing that there is a unique interpolant to show that if you just add up all of the lambda i's without any yi, you're going to actually get the constant polynomial 1. You'll just get, this sum will just equal 1. And if you remember from algebra, we can always divide or multiply by 1 without changing anything. But what we can do is we can factor that L of x out of this sum, out of this lambda I sum. So when we divide by 1, when we divide by this sum and factor the L of x out, the L of x's will cancel. And so we actually just implicitly use L of x. We never need to actually compute it. And this leads to the kind of bizarre looking but beautifully elegant formula equation 7, where all you have to do to evaluate your polynomial is compute these two different sums and then divide them. Now this might seem like extra work, but each term in the sum, only on the top and the bottom, only differ by this yi. So you only need to compute each term in the sum once, as in you need to compute the 1 over wi times x minus xi once, and then on the top you multiply it by y, and on the bottom you don't. So you do these two sums, and then you divide them. And this really cuts down on the number of floating point evaluations that you need to do. There's basically one subtraction here, one multiplication, one division, and then there's an extra multiplication on top. So in total, you do 1, 2, 3, 4. In total, you do 4n plus 1, so 4n plus 4 floating point computations to evaluate this polynomial. So there's a question I don't get, but basically you can't reduce this anymore. You genuinely have to compute these two sums separately, but you can just reuse this computation, the 1 over wi times x minus xi computation, as you're doing the sum. Yeah, and what canceled out in doing this is the L of x that we had on the last slide. This polynomial here, we divided it and it cancels out. This interpolation formula, as I say here, it's bulletproof. Like basically any possible criticism from a numeric standpoint or a speed standpoint that you can have about it is going to end up being fine. It'll work out. It's fine. So it is stable. It requires O of n operations, which we already counted. It's like 4. Actually, it's like 4n plus 5 floating point operations in total. We talked a little bit yesterday about catastrophic cancellation, where you have two numbers that are very close and you take their difference. And you might worry about catastrophic cancellation here. It just turns out it's just not an issue. Not an issue at all. There are whole papers written about how there's no cancellation issues with this formula. And it basically is because the catastrophic cancellation happens on both the top and the bottom, and so they just cancel each other out. And there's no cancellation. The cancellation gets canceled, which is this kind of wonderful result. Now, for actual computer implementations, you do have to check to make sure that your input isn't literally one of the xi's. But this can be done with log n checks if you have your xi's sorted. So that's a trivial computation compared to the ON cost. And if it happens to be equal to xi, you just return yi, because the whole point of this exercise is to make lambda, which has that property that lambda of xi equals yi. So there really are no issues with this formula. Are there any questions about the barycentric interpolation formula of the second kind? All right. So hopping along, we can move on to the next slide. And so again, like the whole point of this formula is to avoid ever having to compute the coefficients or use them to evaluate your polynomial. And in doing so, it's very important to note that by doing all of this, we have not only given ourselves a good algorithm, but a fast algorithm, but we have given ourselves a notably better algorithm for evaluating a polynomial. So it really is just excellent. And if possible, I would almost always work with this formula and with polynomial interpolants, whenever. It also, basically, you also can compute your wi's, your interpolation coefficients, early. Like when you, for instance, if you're in an object-oriented language, when you create the object, you can just compute the coefficients, and then you reuse them every single time. So that's not really a problem either. And it turns out, actually, for some choices of your xi's, because we haven't talked about that yet, but you basically can sometimes choose where your data points are, and if you can, there are some very well-known formulas for the wi's that might save you from having to compute them at all. For instance, we'll talk about it in a bit. There's these Chebyshev weights, and except for the first and last weight, they're just plus or minus 1 every time, which is kind of awesome. Now, yeah, as I said, for my money, except for in very, very specific applications, I've always found that the second barycentric interpolation formula is quite good and is essentially the best way of evaluating a polynomial interpolant. and you shouldn't really bother with any other way. Slide is not, there we go. So this entire time we've just been talking about data points. And at the beginning of the lecture, I promised that we would be using these polynomial curves to approach functions. And so, like, how do we do that? How do we actually use these to approximate functions? Well, if you have a function, one way of getting points out of it would be to just take that function, take some values of x, plug those values in, and then interpolate through those data points. And this is exactly what we're going to do. You just have a function f that we want to approximate using a polynomial interpolant. You plug in a bunch of values of xi to get some yi's, and then you interpolate through those points using the barycentric interpolation formula. And for the barycentric interpolation formula, all you need to save are the xi's, the yi's, and the wi's. With those three lists of numbers, you compute the interpolant every time. You never need to compute the coefficients. You never need to write down the polynomial in any other form. You can just save those three lists and evaluate the polynomial interpolant cheaply and stably every single time. Now you might ask, how should we pick the points? Well, it turns out that this is the most important decision you can make. Where do you sample your function? There are basically two good choices. There are, strictly speaking, more good choices than two, but you'll almost always see these two picked. There's the Chebyshev points and the Legendre points. The Chebyshev points are basically just better. They are cheaper to calculate, like it's cheaper to find which points you should sample, and there are essentially no advantages in practice to using the Legendre points over the Chebyshev points. There are some claimed advantages, and in some very narrow cases, those advantages are real, but it's important to recognize that just because there's a weird edge case where one might work better, mean that on average it is better. And so that basically there are weird edge cases where the Legendre points win, but the Chebyshev grid points are essentially almost always the better choice. And one reason they're like a better choice is I can write them down from memory. They are pretty easy to compute. You just use cosine. All of this other junk around here is just rescaling and reshifting the interval. But the core work of picking the Chebyshev points is this cosine thing right here. And so if you just sample on this set, this list of points, starting with I equals 0 and going to I equals n, you will get what's called a Chebyshev interpolant. And Ethan and I and some other people in the server have a open source math package written for Roblox Lua called RBX Math. And RBX Math has an extensive implementation of Chebyshev interpolation that essentially is plug and play. If you give me a function and you want it to be a certain amount accurate, we can just do that. If you want 10 to the minus 13 accuracy across a whole interval, we can just give you an interpolant that is that accurate. Now, using the polynomial afterward, figuring out how to actually do the math for your problem might be less plug and play, but the actual interpolation process is. Oh, there's a bug. Wonderful. Well, the RBX Math, the interpolation stuff, well, at least on my computer it works. But there's a little bit of an issue between iDevelop and Lua and Luau, and but then people want to use it in Roblox, and so there might be some translation issues. But we're working on making it better, and if you want to make it even better, you can help us work on it. Just let me know. Yes, at least on my computer it works. I know because I use it to do my numerical methods homework. So, I've actually used it to get good grades on a homework assignment. But anyway, I'm very proud of the Chebyshev part. But so now we're going to move on to the last thing I wanted to talk about, which is what I called my unhinged rant. So when I was a young math student taking numerical methods for the first time, I was told some lies, essentially, that have wormed their way into the ethos of numerical methods. One thing I was told is that polynomial interpolation doesn't really have any real uses. I was told that polynomial interpolation is inherently numerically unstable. I was told that high degree interpolation, like meaning degrees over 5, were going to be incredibly squiggly and terrible and would never approximate your function. And these are all false. Almost universally, this is an issue of the author either being unaware of or not mentioning the barycentric interpolation formula of either kind, or they do not have any discussion of the actual act of picking points for your polynomial interpolant. So it turns out a terrible way of picking points is to just uniformly subdivide an interval. Like, this is awful. And yes, if you're doing what's called uniformly spaced points, your polynomial interpolation will be bad. But if you pick Chebyshev interpolating nodes, if you pick Legendre nodes, and if you use the barycentric interpolation formula, all of these woes and all of these problems just vanish into the ether. There are some very small problems, but in majority of the cases, and in for all quote nice functions, which is most of what we encounter in our life and in application, polynomial interpolation is a fast, stable, and powerful method of approximation. So don't buy into the hype. Polynomial interpolation is actually good. And something on the slide, another great thing about Chebyshev interpolation, it will essentially tell you if the interpolation is bad. There is a way with Chebyshev interpolation to essentially estimate the error between your true function and your Chebyshev approximation, and it'll just basically tell you straight up, this is bad, or this has highly oscillatory behavior. And so you can just compute the approximant, and if the approximant doesn't work, you have these, well, they're not quite guarantees, but they're these soft guarantees of convergence and non-squiggliness. And again, RBX math can basically approximate a function to any degree of accuracy. And I have worked with polynomials on with degrees on the order of 10,000. It's been perfectly numerically sound and relatively fast. Now, if you're going into the 10,000 range, that's still like 40,000 computations. So that's not going to be fast by any means, but it still works, and we should not be judging polynomial approximation as this kind of thing that should never be used. Tomorrow we're going to be talking about spline interpolation, which is basically the answer to, well, what if I am worried about these edge cases in polynomial interpolation? Or what if I really need it to be extremely fast and I don't really care as much about accuracy? And so that's going to give us spline interpolation, but that spline interpolation should ideally be thought of as the little brother of polynomial interpolation, and instead of as the gold standard. So, are there any other questions about any of this stuff? Polynomial interpolation.